So there's three subsystems. We have a control unit, we have an ALU, an arithmetic logic unit, and then we have input and output unit, so I/O lines. That's how we perform the addressing, is through I/O lines. So then we also have registers, and we have codes, we have clocks, and we have clock speeds. So the clock speed, you might tell it, I want you to operate at this speed, or I want you to kick it up and we're gonna overclock. You know, that's what the clock speed's about. Not all processors have a tunable clock speed, but internally it's set by something. And then usually with the crystal, the clock is set with some kind of a crystal that oscillates. When power is applied to it, it clicks off at the same time over and over and over and over. And then there is some drift where every now and then it'll speed up for a second and slow down. But not even for a second, right? It's like a fraction of a fraction of a fraction of a second. We have to kind of reset it. And we know what the drift is because it's predictable mathematically. So every so often we can just reset the time in the computer because we know we're drifting at this rate. So that's what drift is about. And then with respect to registers, they're just going to hold information for a certain amount of time, right? So that's a transistor. I'm going to turn that transistor on, and if I have this transistor and this transistor and this transistor on, that means something logically inside the computer, whatever you want it to do, right? And then with respect to codes, we have these things called opcodes, or operational codes. So every processor comes with a set of opcodes. And opcodes might mean add two numbers. A certain opcode means add these two numbers. Another opcode might mean it might have two operands. The operand might be an address location, like a memory location, and the other one might be a read or write. So you're going to take an opcode of a memory address, and it might be load. Like, for example, there's an opcode for a load effective address. So we want to take this memory location and load it into this register, right? So the registers are inside the CPU. They have X amount of them, and that's so things can happen fast, right? So the memory operations take time. I have to go outside of the chip to the memory and then bring that stuff in, and that takes time compared to operations that happen locally inside the CPU. So I can be running a whole lot of operations while I'm preparing for the next set of operations. So I might load an operation, and while that operation is being performed, I'm loading the next one, and that's kind of how they work. So that's what the cache is about. So you have the external, so let's just say this is the computer, right? And then we have the cache, which is closer to the CPU, and then we have the actual CPU. So the farther out you go, the longer things take. So we get to the cache, which is incredibly fast relative to the CPU, and then inside the CPU, it's incredibly fast. So inside the CPU, things happen just faster than you can believe. So now we have memory. We're going to talk about memory. So we have the external data bus, and then we have the processor chip, which is connected to that bus. And then we have the memory controller chip, which contains the address bus. And then we have the RAM, which is electrically connected to the external data bus. So what that means is you just have an electrical line of copper that goes to and from the RAM for the external data bus. And now you can see how the address bus comes into play. I'm going to light up certain lines with power, and the rest of them will be zero. And that memory chip controller is going to figure out, okay, the processor is trying to write or read from this memory location. So the address bus, the way those lines light up, whichever ones are lit up versus down, tell the RAM which memory we want to read or write to, and then also whether or not we're going to read or write. So it gives it literally the address that we're trying to go to or from, and then what operation we're trying to do, which is a read or write. So that's kind of how this works. So depending on what signals are on those lines determines the address and the operation, read or write, with respect to RAM. So how microprocessors work. So this is one model, right? So that could be the DMA, the direct memory address. There's other ways to do it as well, but this is one model. So how microprocessors work, we have fetch instructions, we have instruction decode, which happens in RAM, and then instruction execution. So we have a fetch, a decode, and then an execution. So we talked about all kinds of representation. That's where the decoding comes in. And then the fetch, so that's what the cache is about. You know, things are put into the cache and they're ready to go, they're decoded, and then the instruction just executes them. You know, that kind of thing. So again, there's no one-stop model. All the processors do it a little bit differently, right? So these are the things that can happen depending on the specific implementation that we're discussing. So PC personal computer, PC microprocessor developments and features, they use the following elements to gauge CPU performance. So we have to measure it somehow. What is the model we're going to use? So we use speed, processor speed, like literally how fast does this thing tick? How fast can we clock it out to? The number of transistors, the number of registers, the external data bus, and the address bus, as well as an internal cache. So today's CPUs have internal and external cache. And the cache is very expensive. It's incredibly fast RAM.